Hello and welcome back to section 1.3. In this video, we are going to talk about convergent sequences and the relation to the closure of a set. We're going to talk about limit points and the boundary of a subset of R. Okay, so let us first revisit the notion of a convergent sequence. If you have a sequence in R, xn, and a point x in R. What do we mean by saying that xn converges to x? And we write in this symbol, or limit of xn equal x. Well, you can say xn converges to x means that xn approaches x, right? But this is not so precise. A better definition would be of convergence would be xn can be made arbitrarily close to x. Arbitrary means as close as we wish to x for all n large enough. Okay, so this is the definition. Xn can be made arbitrarily close to x for all n large enough. Okay, for all n large enough means starting from a certain rank. Okay, now what do we mean by xn can be made arbitrarily close? It means that the difference between xn and its limit can be made arbitrarily small starting from a certain rank. Otherwise stated, this difference can be made less than any positive number we like, starting from a certain rank. And this is how we come to the definition that you probably learned last semester or in school. For every positive epsilon, there exists a certain rank n0, starting from which the difference is less than epsilon. So you can think of epsilon here in this definition as being the accuracy of the approximation. If xn approximates x, or x approximates xn, it means we have to specify the degree of accuracy. Epsilon is the degree of accuracy. So for example, if you take epsilon equal 10 to the power minus 3, it means that the first 3 digits of xn coincide with the first 3 digits of x. Okay? If we take epsilon equal 10 to the power minus 9, it means that the 9 decimal xn and x have the same 9 decimal places. Okay? Decimal numbers. We can also restate this in the following way. So for every epsilon positive, starting from a certain rank, n0, xn will be in the interval x minus epsilon, x plus epsilon, for n bigger or equal than n0. Okay? Now, since x minus epsilon, x plus epsilon is a neighborhood of xn, and every neighborhood of x minus epsilon, x plus epsilon is a neighborhood of x, and every neighborhood of x contains such an interval x minus epsilon, x plus epsilon. So we can restate this condition in the following way. Every neighborhood of x contains xn starting from a certain rank. Okay, so all these ideas are equivalent, if you like. So usually we take this line as the definition, but don't forget that it's a precise mathematical translation of this idea of approximation or approaching. Okay, so we approach x by a sequence xn. And now, having reviewed the notion of convergence, we can give 3 equivalent conditions for a number to belong to the closure of a set. If you have a set A, it's a subset A of R, and a number x in R, then we have 3 equivalent conditions. The first condition states that x is in A bar, is in the closure of A, which is by definition what? It's the smallest closed set containing A. Second condition, every neighborhood of x meets A or intersects A. And third condition, there is a sequence in A converging to x. Okay, so these 3 conditions are equivalent. Okay, this is not so easy. The proof that one is equivalent to 2 will be made, because it's difficult actually, will be given in the course, the topology course, Math 2201, next year. And even second year students find it difficult. Okay, so I'll not give the implication, the equivalence between 1 and 2. Rather, I will prove 2 implies 3. Okay, so because this is not really a course in topology, this is just an introduction to the topology of R, but you should know these properties. Okay, so in some sense, A bar is not very far from A. It's really glued to A in some sense. Okay, so points in A bar really can be approximated by points in A. Okay, so this is why we call points in A bar adherent points. Okay, they are really glued to A. So let us prove that 2 implies 3. By assumption, every neighborhood of X intersects A. So in particular, if for any positive integer, the interval x minus 1 over n, x plus 1 over n, it's a neighborhood of X, should meet A, should intersect A. So therefore, but this is true for every n. So for every n, I may choose a point in the intersection between this neighborhood and A. Okay, and call this intersection point xn. Okay, so take xn in the intersection. Then what happens? Then by constructions, we have a sequence in A, because xn by construction is in A, and xn is here. So its distance to x is less than 1 over n. Okay, so what do we have? So when n tends to infinity, this tends to 0. Okay, so this can be made less than any epsilon I like, if I choose n big enough. Okay, so it means that I found a sequence in A, xn, converging to x. But note that x did not belong to A unless A is closed. Okay. Now, 3 implies 2. Suppose that there is a sequence in A converging to x. Okay, and let U be a neighborhood of x. We have to prove that U meets A. Now, since xn converges to x, we know by the previous discussion that starting from a certain rank n0, xn will be in U, right? So take, for example, xn0. xn0 is in U. And xn0 is actually where? It's in A. Okay, right? Because we have a sequence xn in A converging to x. Okay, so xn0 will be in A and in U. So it is in the intersection of U and A. Okay, here we take xn in sequence in A. Therefore, the intersection is not empty. And this is precisely what 2 means. Okay, so we prove that 2 is equivalent to 3. Now, let us draw some consequences out of this result. Suppose that we have a sequence xn in A, and A is a subset of R. And suppose that xn converges to x. Now, x did not belong to A, but it's not very far from A. It's in A bar. So yeah, so since x is in A bar, okay, this is the first thing, right? So in particular, if A is closed, then x belongs to A. This is what I said before, okay? And probably this is one of the reasons why we use the adjective closed. Closed, it's closed under the operation of taking limits. So if I have a sequence in A, the limit, and A is closed, the limit cannot escape, cannot be outside A, it's still in A. Okay? And it's not true if A is not closed. Okay? Can easily give counterexamples. Okay. Now, another consequence is that the closure of Q bar is what? Is the whole line. We stated this as an example earlier, but we didn't prove that. Now I'll give 2 proofs of it. One relying on proposition 1.6, and one not relying on it. So let us go with the first proof. Okay. How do we prove that 2 sets are equal? Double inclusion. Now, Q bar is in R because we live in R. Okay? because by definition Q bar is a subset of R. So Q bar is contained in R. So we just have to prove that R is contained in Q bar. How do you prove that? We take an element X in R and prove that it is in Q bar. So take X in R. How do I prove that X is in Q bar? I use proposition 1.6. So let U be a neighborhood of X. We have to prove that U meets Q. Okay, but since U is a neighborhood, it's an open, we can take it open if you like, but it's a neighborhood. Since U is a neighborhood of X, what does it mean? It means that U contains an open set containing X. And since X is in that open set, then by definition of an open set, there is a whole interval around X of the form X minus epsilon, X plus epsilon, or you can call it X minus delta, X plus delta, contained in that open set, and therefore contains in U. Okay? So, what do we have now? The interval X minus epsilon, X plus epsilon is contained in U, right? And this interval contains rational numbers, because we know that this is a fundamental property of R. Any non-trivial interval contains rational points and also irrational points. So since it contains rational points, so it meets Q, right? So we proved that U meets Q. Therefore, for every neighbor, U was arbitrary. So we proved that every neighborhood of X intersects Q. And by proposition 1.6, X belongs to Q bar. Okay? So we are using the implication 2 implies 1. Okay? So this is the first method of proving that Q bar is R. Now there's another proof that doesn't use proposition 1.6, just go back to the definition. Okay, so second proof. Okay, I'll go back to the definition. Suppose that B is a closed set containing Q. Then the complement of B is contained in the complement of Q, right? Now, if B is closed, the complement of B by assumption is open. So we have an open set inside the irrational numbers. Okay, this is an open set contained in the irrational numbers, right? So it could be empty, but could not be empty. Well, let us see. Could it be not empty? Well, if it were not empty, it would contain a non-trivial interval. But there's no non-trivial interval is totally contained in the irrational numbers, because every non-trivial interval contains rational numbers. Okay, so we have to conclude that R without B, which is an open set, must be empty, right? And if R without B is empty, it means that B equal R. So what did we prove? We proved that there is only one closed set containing U, which is R. Okay? So the collection of closed sets containing Q contains just a singleton, B. B is not a singleton, but the collection consists only of one element, which is B. So the smallest such example is the smallest element of this collection is B, of course. So we conclude that B, which is R, is the closure of Q. Okay. Now, arguing in the same way, we prove that the irrational numbers, the closure of the irrational numbers is R. Otherwise stated, the irrational numbers are dense in R. Same reasoning. Okay, you can either use this proof or this proof, same thing. Okay, but that's actually still the same idea. Okay, which is the fact, we're just using the fact that any non-trivial interval contains rational numbers and contains also irrational numbers. Okay, unless it's empty. Next, suppose that A is a subset of R and X a number in A bar. Okay, we are going to classify the elements of A bar, right? By proposition 1.6, we know that every neighborhood of X meets A. So we have two types of points in A bar, okay? So we have two possibilities, okay? Two mutually exclusive cases. Okay, first case, there is a neighborhood U of X which meets A only at the point X. It's possible. It's completely possible, and we can easily give examples. Okay. So otherwise stated, some neighborhood of X meets A only at X, right? What is the negation of this case, but assuming still that X is an A bar? Okay, so every neighborhood of A meets A. Okay, what is the negation of this? U intersect A is not equal to X, but it's not empty neither. So what do we mean? We mean that if this means that U intersected with A without X is not empty. Or if you like, yeah, but just notice that in the first case, X is in A necessarily, okay? Because X is in the intersection. So necessarily, okay. The second case, the negation of this is that every neighborhood of X meets A at a point different from X. Okay, so this is actually the negation of this, but under the assumption that we are in a bar. So in both cases, U intersected with A is not empty. Now, it could consist, the intersection could consist only on one point, or contains another point than X. Okay, I will give examples now. So in the second case, we need not have X's in A. Okay, now I can give the following definition now. In the first case, we say that X is an isolated point of A. In the second case, we say that X is a limit point or an accumulation point of A. Okay. Let us give some examples. Consider the set A consisting of the open interval 0, 1 and with the singleton 2, right? Okay, what is a bar? You should agree that a bar is 0, 1 closed, union 2. Okay? So, okay, what are then the limit points of A and what are the isolated points of A? Any point in 0, 1 closed is the limit point of A. Why? Because just do a picture. If you take a point or an element in 0, 1 closed and consider any neighborhood of that point, then it meets A at a point different from X. Okay, just because an interval contains infinitely many points. Okay, the intersection of two intervals. Okay, whereas 2 is an isolated point. Why? I should have drawn a figure, but you do it. Consider, for example, how do you prove that 2 is isolated? Consider the open interval 2 minus 1 half, 2 plus 1 half, okay, which is 3 half, 5 half. Okay, 3 half, 5 half meets A only at 2. It doesn't touch 0, 1. Okay, so 2 is the only isolated point of A. And this is not the case for all points in 0, 1 closed. Okay. Another example, any finite subset of R consists of isolated points. So otherwise stated, a finite subset of R has no limit points. Well, how do you know that? Just draw a picture if you like. Okay, suppose that A is of the form x1, x2, x3, xn. Okay, it's a finite sequence. Okay, and we can assume that all the points are distinct. Fine. So for each I, for each index between I and n, let Ri be the distance, or if you like, the distance between xi and the set A without xi. Okay, so if you like, consider the point xi. Among the remaining points, there is one closest to xi. You can call it xk if you like. Take this to be Ri. Okay, so what does it mean? First of all, Ri is positive because we assume that the points are distinct. Okay. Now, if you like, you can take Ri over 2, if you like. But this is really the biggest such So the interval xi minus ri, xi plus ri, meets A only at xi. Because why? Because if j is different from I, j cannot be here, because the distance between xi and xj is bigger or equal than ri. So no xj for j different from I can be here. Okay? So the intersection consists only of xi. Okay, try to make a picture. Just take 3 points, x1, x2, x3. Okay? And so we proved that, so we found a neighborhood of xi meeting A only at xi. And this is true for all I. So all points in the set are isolated. There are no limit points. So what does it mean? It means that if a certain set has a limit point, it must be infinite, right? Okay, consider now an infinite set A, which consists of the numbers 1, 1/2, 1/3, 1/4, okay, and so on. Okay, so what happens now? I claim that all elements of A. So what is A bar actually? We can prove that A bar. So A is not closed, but A bar is A union 0. Now I claim that all elements in A are isolated, and 0 is the limit point of A. And 0 is not an A, it's an A bar. Okay, how do I know that? Okay, try to prove that. Why 0 is the limit point? Because if you take any neighborhood of 0, so it contains a certain interval of the form 0 minus epsilon, 0 plus epsilon. Okay. Now, in the open interval 0 epsilon, if n is large enough, then 1 over n will be between 0 and epsilon, right? So it means that this neighborhood of 0 meets A at a point different from 0. Okay, 1 over, let us say, m for m very large. So 0 is indeed a limit point. Now, why all other points are isolated? It's not difficult, because essentially because between 1 over n and 1 over n plus 1, or the other way around, there are no elements in A. Okay, so there is a certain distance between the elements of A. It could be very small, but still is positive. So, for example, if you take the interval, for example, 1 over n, okay, and consider the open interval 1 over n plus 1 and 1 over n minus 1 open. It meets A only at 1 over n, because between 1 over n plus 1 and 1 over n minus 1, 1 over n is the only element in A. Okay, so try to do a picture actually. So therefore, actually, all points of A are isolated. Okay, and 0 is the only limit point of A. And you can prove actually, try to prove that if x is the limit point of A, then not only every neighborhood of x meets A at a point different from x, but actually it contains infinitely many points. Okay, and this is true. You can check that. Okay, for example, in this case, the interval minus epsilon epsilon contains all n from a certain rank. So and this set is infinite. Okay, here same thing. If you take 1 minus epsilon 1 plus epsilon, there is a whole interval in the intersection, so it's infinite. Okay. Now, last thing in this video is, what do we mean by the boundary of a set? The boundary of a set A, and usually we use this notation, partial A or del A. This is a widespread notation for the boundary. Is what? Is the closure without the interior. And the elements of A are called boundary points. Okay, let's give some examples. What is the boundary of the interval 0, 1? Okay, we apply the definition. The closure of 0, 1, 0, 1 is closed, so the closure is itself. The interior is the open 0, 1. And what is the difference? The difference contains only 2 points, 0 and 1. So this corresponds to our intuition that 0 and 1 are boundary points of the interval. Now, unfortunately, not all subset of R are intervals. So the boundary can be something complicated. Let us see examples. And of course, we can take any kind of interval. There are 4 cases. We can take 0, 1 open, 0, 1 semi-closed, semi-open. We get exactly the same result. Okay. Now, less trivial example is the boundary of Q. What is the boundary of Q? If I go back to the definition, I get Q bar without Q circle. Now, Q bar, we prove that Q bar is R. And we proved in an earlier video that Q circle, the interior of Q, is empty. So it's just R without the empty set, and which is R. Okay. So the boundary of Q is the whole line. Okay. And for a similar reason, the boundary of the irrational is also R. Same reason. Okay. Now, I will stop here. And in the next video, we are going to talk about the very important notion of compactness. Okay. And related concepts. So thank you for your attention.